Hello guys, welcome to our course Computer Architecture 2, 3 to 40. This is Dr. Mustafa Abdirahim, the instructor of this course. So we're gonna teach this course from the famous book by David Patterson and John Hennessy, Computer Organization. And we're gonna start just like the book started by the 8 great ideas, in the field of computer architecture. So there are 8 ideas, that dominates this field of science or engineering. Okay, and basically these ideas are really old. At the same time, they are really very influential and they still used to this day. Okay, and the very famous idea and the very first one basically is design for Moore's law. I'm not saying Moore's law. I'm saying design for Moore's law. So as you know, guys, Moore's law states that the integrated circuit resources, basically the number of transistors, doubles every 18 to 24 months, between 1.5 years to 2 years. Let's say 2 years. So the idea here, not the law itself, but the idea here is to use this law as a fact and start to modify the design such that you abide to this law. So for example, let's say you're gonna have a design. This design to be completed, it may take like 4 years. So if we can put 1 million transistor currently, okay, that means after 4 years we're gonna have 4 million transistors, because if you're gonna double each 2 years, so after 2 years you're gonna have 2 million, and after 4 years we're gonna have 4 million. So if with 1 million transistor you can do or design one processing cores, then we can say, roughly with 4 million transistors we can design in the same chip 4 cores, so we can have parallelism, So, and that's the idea of design for Moore's law. So anticipate all the time what will be, the resources available by the end of the design, then adapt or modify your design so that you can use these extra resources that you're gonna have naturally according to Moore's law. Okay. And here is, if you guys can see, this is just to show you that Moore's law really work. Okay, and it's really linear. So here on the x-axis you have the years, and here on the on the y-axis you have the the number of cores. And we can just draw here a line, a fitting line, a linear fitting line, that really passes through all such designs that we had, all over the years. Okay, so it's really working, and you should really use it. Second idea is use abstraction to simplify the design. So basically, abstraction, here means if you have a processor, don't look at the processor as a one-wall atomic module or circuit to implement. That means, you're gonna design, all, or one team basically in the company will design all the processor at the same time. That's not gonna work. Because if you let's have another scenario. If you if you divide the circuit into sub-circuits, sub-modules, the processor sub-modules, and you assign to each team, or you divide your team into also multiple teams and assign for each team one of these modules, and look at the module as specifications, like the performance of this module. Like for example, a memory module, you want a memory with let's say a delay, an X delay or Y delay, something like this, area equal to whatever, power consumption equal to whatever, and then you give this specification to the design team, and the design team will work and do some stuff, some engineering design to implement a memory with such a specification. You as a manager, for example, you don't care about, or you don't give much care about the level of details that this team done for you, but you just compare their output to the specifications that you gave them in the first place. So by that, your teams, in the company can work in parallel to design your to design your processor. And that's basically one advantage of having abstractions in your design. Okay. The third example is making common case faster. Okay, so making common case. Let's assume you have a processor. This processor is consume 80% of its time doing addition instructions and 20% doing multiplication. Okay, so and we can improve both. We can improve addition and we can improve multiplication. Okay, but let's say you have only a limited time and you can apply only one improvement, either through the multiplication or the addition. Okay, let's say you have an operation. This operation takes, with the original design 10 seconds. Basically 8 seconds is for the addition and 2 seconds for the multiplication. Okay, let's say that the improvement in the multiplication is 100%. So basically, of course, this is an imaginary case, that you can improve the multiplication delay by 100%. Basically, you can reduce the delay goes to the multiplication circuit by 100%. It makes it making it 0. So in that case, the operation that takes 10 seconds, 8 seconds addition, 2 seconds multiplication will take only 8 seconds. Basically the addition, because multiplication now takes 0 seconds. Okay, this is 20% improvement, which is good. That's not bad. Let's now have another improvement that you can also apply. Okay, which reduces the delay of the addition by 50%. So in that case, you have again 10 seconds multiplication, 8 second addition. Okay, now the addition takes only 4 seconds. So in the new design, you have 4 second addition, 2 seconds multiplication. So you have in total 6 seconds. 40% reduction in the 40% reduction in the execution time. So which is better? When we did 100% improvement in the multiplication, we reduced the execution time by 2 seconds. But when we do just a 50% improvement in the common case, in the addition instructions, we get 4 seconds reduction, which is translated to 40% reduction in the. So that's the basic sense behind the common case reduction, or making the common case reduction faster. Good. The fourth, great idea is performance via parallelism. Okay, and by the way, here the book gives each idea of those an icon, and the icon for parallelism is a jet plane. So let's assume with 4 motors here. Let's assume for engines, if you have one engine, you can go, for example, 100 miles per hour. But when you have 4 engines, you can have 400 miles per hour. So that's basically increasing the performance because you have 4 engines running at the same time in parallel. So in processors, we have many levels of parallelism. We can have instruction level parallelism. So let's say you have an instruction like A equal to B plus C and Z equal to Y plus Z. These 2 instructions are not dependent. So I don't have to wait for the first instruction A equal to B plus C to finish to execute the second instruction Z equal to X plus Y. I'm sorry, X plus Y or Y plus X. Okay. So basically you can run these 2 instructions in parallel. Of course, provided that you have logic circuits in your processors that can do this in parallel. But even with this, we have another level of parallelism, which is called data level parallelism. Let's assume now that A is vector, B is vector, and C is vector. Like this is an A vector, 2 elements. B is another vector, 2 elements, 1 and 2. And C is another vector, 2 elements, also 3 and 4. So basically the result will be 4 and 6 here. Now the first addition again can be done in parallel with the second addition. This is called data level parallelism. So inside so it's another level of parallelism. After doing the instruction level parallelism, we can even do data level parallelism on the instruction, one instruction itself. Okay, so that of course can boost the performance more. The task parallelism here, which is basically the most obvious one, we have PCs nowadays. These PCs, personal computers, they have multi-core processors, and we usually when we open and turn on our PCs, we run multiple applications, like for example Zoom, PowerPoint, word processing. So each one of these has different task, and if you have multi-core, then you can run each one of these in a separate core. So to have a task parallelism here. Another example, maybe not so obvious, is what's called bit level parallelism. So we hear that there are computers with 32-bit processors and another computers with most of now is 64-bit processor, but we still see 32-bit processors. Okay, and here we increase the data width or the bit width of the processor itself from, for example, 32 to 64. So let's assume you have a variable, two variables, like for example a equal to b plus c again. A is 64 bits and b and c all are 64 bits. But your processor is 32 bits. So in that case, to add b and c together, you should do this in two steps. Like two instructions, basically. Like if you have two instructions, one instruction to execute the least significant 32 bits of B and C, then another instruction to make the addition for the most significant 32 bits of B and C, and then combine, the result in A. Okay, but if you have from the beginning a 64-bit processor, you can do this instruction in just one step. That's basically bit level parallelism. The fifth great idea is performance via, or increasing performance via pipelining. Okay, so when we talk about parallelism, we implicitly assumes that you have a redundant hardware that, and or an extra hardware that can do the same job. So for example, let's take very related but very far away, it's not processors at all, example of a washing or a laundry, basically. So in a washing or a laundry, you wash, you dry, you fold, you put your clothes in a wardrobe, for example. Okay, or iron is in folding in a wardrobe. So one process is divided into 4 operations, and if you're gonna go in series, user A for the laundry will, for example, start at 6 p.m. and finish at 8 p.m., 2 hours, assuming that each operation is half an hour. Then user B comes at 8 and finishes by 10, and so on. So until user D. So in total we have here 8 hours. Each user's 2 hours, then we have 4 users, then 8 hours. With parallelism, we can, if you have 4 times the resources, if you have 4 washing machine, 4 dryers, 4 irons and 4 wardrobes, for example, or whatever, then you can do all this in parallel in 2 hours, because A and B and C and D users can work at the same time. But here we have extra 4x the cost. Pipelining is an idea that can increase the performance, okay, at the same time you don't increase the cost. So let's go back to our example again. So A came at 6 p.m., uses the washing machine for half an hour. So at 6:30, user A will use the dryer, and the washing machine become empty. So why not user B come at 6:30 and use the washing machine? So while user A is using the dryer, user B will use the washing machine. Then at 7 p.m. B finishes the washing machine, A finishes the dryer, so C can come and use the washing machine, B can use the dryer and A can iron, for example. So we have now parallelism, right? That's parallelism. So this is basically pipelining. And in total, we consume here 3 hours. Yes, it's more than 2 hours, but it's not 8 hours. And we don't increase the cost. We have one washing machine, one iron, one dryer, you know. So we don't increase the cost. That's basically the idea of pipelining. Number 6, performance via prediction. So there is a concept of pipelining bubbles. Basically, if you have two dependent instructions, like for example A equal to B plus C, then Z equal to X plus A. So these two instructions cannot run in parallel because this instruction 2 must wait for the first instruction A to finish, then it can go forward and execute the second instruction because it's dependent on the first instruction. That creates what's called the bubbling in the pipeline. Okay, so of course in the processor we don't have like a washing machine and the dryer. We have stages also, something analogous to the laundry, like analogous to the washing machine, the dryer, and the folding and stuff. And these 5 stages basically it's called the folding. Fetch, decode, execute, memory, write back. It's not time now to give you explanation for each one of these steps, but you can think of them like a washing machine, a dryer, and folding or ironing, then folding. So mean separate resources, separate circuits. So when you, for example, do decoding, for example, for the first instruction, you can fetch the second instruction. So this is the first instruction, this is the second instruction. But because of the dependency, okay, you might have what's called, you might stop until some instruction finishes, like here we stop for instruction 1 until so that we can execute the second instruction. Here we have the same. This is basically assembly language. You don't have to worry about what's really meant by this assembly language. It says x86 assembly, but that's not our topic now. But basically here we are saying sub AL, and AL is a register that contains a value. So we're gonna subtract AL from 8. So if AL is 8, equal 8, consider AL like a variable. So if 8 minus 8 would be 0, so in that case we're gonna jump 0 to high. I'm gonna go to this line here that have the label high. But in order to know if we have really a subtraction that causes 0 or not, we must wait until this instruction to finish by after the 5th stage, the write back. Then we can continue with the second instruction, making the decode, execute, memory write. So this is the dependency creates bubbles here. Empty cycle that doesn't have executions. But then here another type of bubble will come. Since we don't know where to go, either to continue forward or to go to high, we must wait until cycle 9 here, the end of cycle 9, so that we know either we will continue and execute this instruction, move BH and 4, or go to the line starts with high label and move BL and 7. BL and BH, by the way, it's just registers. Consider them as variables like A, X, Y. Okay? So again, we created 4 bubbles here. So I'm saying here that let's assume that AL has 8 before instruction 1. So in that case, we will have 0 subtraction. So we're gonna jump. If 8 is 10, for example, this is not 0 subtraction. So we're gonna execute the third instruction. In either case, we have to wait until the 9th instruction to execute the 4th instruction. And this will create 4 bubbles here. One way, and this is really, a common case in our programs. Our programs usually have if-else statements, like if condition do this block, else do another block. That's basically branching. That's like jump zero high. That's exactly similar. So and also the for loop. Let's say we have for loop for I equal to 0, I less than, let's say, 1 million, I plus plus. So in each iteration we compare the current value of I and 1 million, and if it's really equal to 1 million, we will not execute the for loop block anymore. We're gonna skip to the statement after the for loop. So that means for at least 1 million bubble, we're gonna introduce 1 billion bubble into the pipeline. That's really not efficient. Okay, that's why we have what's called the prediction. So the idea of prediction: can you predict whether I will be equal to 1 million or less than 1 million in advance? And if you could predict this, correctly, then if you could predict, for example, here, if we could predict correctly that we're gonna go to high, then we can decode, execute, memory, write back, and finish by the end of the 10 cycle. So we're gonna finish here with good branch predictor. And there are many techniques for branch predictions, okay, that can give you very good accuracy. So here, without branch prediction, we finished by cycle 14, after cycle 14, or we take 14 cycles to execute the four instructions. But if you have a good branch predictor, you can finish just after 10 cycles. The seventh idea is hierarchy of memories. So let's assume you have a program. This program have, so you have a processor, and you have a program. This program have, CPU here, have, for example, let's say 100 variable, that deals with. Okay, so this CPU needs a memory with at least 100 variable, 100 location, okay, nearby. So whenever it needs one of these values, it communicates it to this memory and read back the value of the variable. How about if you have an array, and this array or a matrix, and it has 1 million elements? Then you should increase, of course, let's say 1 million here. We should increase the locations by 1 million. The problem here is that if you have a bigger cache or bigger memory, yes, you're gonna have what's called more hits. You find all what you need there, but you always hit. Hit means whenever you request for a variable, you find it in the memory. Okay, but the problem is that this is a good thing. The bad thing is bigger memory means more delay to read or write. So from one point you increase the performance, from another point you will decrease the performance. That's really bad. And also more energy, because you have more circuitry. We're gonna go in details when we talk about memories in this course, about how much, what kind of power we consume, to read from a memory. So to solve that problem here, what we do is usually we have a hierarchy of memories. So we have a first layer memory that usually implemented with the CPU on the same chip, same processor chip. This is called the cache. It's very small usually, but very fast. Very small, but very fast. Very small and very expensive, by the way. We're gonna also in the future know what I really meant by expensive. So that's the first level of memory. Usually this one here. This is the first level, the highest level. The second level is your dynamic RAM. That's usually bigger, and it's usually outside. It's another chip on the motherboard. Okay, that's usually much bigger, maybe 16 giga or something, or 8 gigas byte. Okay, so whenever you request for a variable that is not located in the cache, this is called the miss, cache miss, and in that case you're gonna ask the memory to provide this variable for you. But of course, it's another chip and bigger memory as well, so you're gonna consume more delay and more energy to retrieve or to read this data from the bigger dynamic RAM memory. Let's say you have more, you are dealing with files, for example, and you have very big data files that maybe exceed 16 gigabytes. Let's assume so. In that case, the dynamic RAM will be not enough. In that case, then you're gonna have what? You're gonna communicate to the hard drive, the HDD. And that's of course much more delay. So that's much bigger. That's maybe in tera, 1 tera, for example. Many hard drives nowadays, just minimum is 1 tera in size, 1 terabyte. But much slower. So that level here is the fastest, but the most expensive. That and smallest as well. So small, expensive, but very fast. The level here, the HDD, for example, here, slow, very slow, but cheap to implement, and biggest. That's the levels of memory. That's one form, by the way, that's one form of memory hierarchy. There is another form, by the way. Let's give you some idea about this another form. So I'm gonna remove this. So there is another form of hierarchy between the caches themselves. So let's assume that you have like a multi-core processor. So a processor of 4 cores, for example. So each core has its own cache implemented very close to it. And this is called L1 cache, level 1. Okay. Then there might be in the same network, on the same chip. Here is the same chip, by the way. I'm talking about the same chip. Another module that is called L2 cache. So L2 cache is bigger than L1 cache, but slower than L1. And you might also have L3 and so on. Usually you have L1, L2, L3, then the dynamic RAM. I mean, the last level here is L3, and the first level is L1. Finally, the 8th great idea, dependability via redundancy. Let's take first, explore the icon. So this tractor, truck here, it has, 2 wheels. So if one wheel become flat, then we can easily go we can still continue our journey and go to a tire shop and replace this tire flat. But the journey will not stop. But if you have just one and this one goes flat, that's it. You must stop, you must call for another tractor to track you or fix this, and basically you cannot continue your journey or your trip. That's basically the idea of dependability. So you want to be sure all the time that your system is working even if some failure happens. And this is an old idea as well that's still used till today. For example, you know, in the Apollo programs, you know, the spaceship capsules, they have processors, and usually there are, you know, in these processors are just spare processors, spare cores. So if the working or the operating processor core fails, you can switch to this core and use it. That's one example. Another example is in data centers. So if you have some data and you store it in a data center, you don't store it in one hard drive. You might store it in multiple hard drives, at least two. So same data is stored here and here at the same time. So that if one hard drive fails, you still have the data on the second hard drive. So you can go and buy another hard drive to replace the one that's failed, to continue using the idea of redundancy, to continue be so that your system, you know, still become or you know, reliable or dependable for you. Okay, guys, that was basically the 8 great ideas in computer architecture, and you're gonna see, by the way, throughout our course, these ideas applies still till today, you know, in all fields of computer architecture. And that's really amazing because these ideas are old, at the same time they are still used. Okay guys, thank you very much for watching this video, and see you in the next video. Bye bye.